Welcome everybody to this one of the first on-site conferences at the new SwissMAP research station. Well, maybe we should warn you that especially for online participants, this is a little bit of a test run, and therefore, I mean, please complain if the quality is insufficient. It may happen in any event. For most of the speakers, as I understand, the recordings will be available at some point, probably this week, maybe. For a moment, for online participants, you would need to ask questions through the chat. So we haven't enabled yet the possibility for people to ask questions in the regime, so as we hear what you're saying. Okay, this said, I'm very happy to introduce our first speaker, Lisa Piccirillo, who's going to speak on not concordance and for manifolds.
Thanks. Thanks so much for having me and for being here. The last time I gave a chalk talk was in Oberwolfach in the end of February of 2020. So I hope, one, that I haven't forgotten how to do this, and two, that you'll believe that I'm really very happy to actually be here and doing this again. I also want to start off by saying that I think I think this is true. My background's a little different maybe than that of many people in the room, so please don't hesitate to ask questions, or if I say something that I think is like a given and you're like, what is that? Please give it to me, especially people in the virtually as well. And holler at me if you can't see anything, etc. Also, this is 2 hours, so there's a lot of notes here, but we can really take the pace like as we need. So please don't hesitate to stop me and ask anything. So the motivating thing I want to try to do today is tell you a little bit about some questions I'd like about four-manifold topology and how this field of knot theory called knot concordance can help you get a handle on these four-manifold problems. So let me start off by telling you just a couple of basics about knot concordance. And let me start that by reminding you that in classical knot theory, we say that a knot, knots are always going to be S1s embedded in S3. We're going to say that a knot is trivial, or the unknot, if it bounds a disk. So what you should have in mind is maybe your knot is something like this. And this is the unknot because it bounds this like bow tie noodle disk in 3 space, like that. Okay, so that's what trivial knots are in classical knot theory. And knot concordance is really born out of just mildly weakening this definition. So in knot concordance, our knots are still the exact same object. They're still S1s embedded in S3, which you just think about as 3 space. We're going to say that they're trivial, or slice. Well, again, if the knot is the boundary of a disk, the only thing we're going to change is where this disk lives. So now I'm going to let this disk use a little more space. It just has to be embedded in B4. And so I can't draw you a sort of exact picture of this, but the schematic you should have in mind is, here's your 4-ball. Its boundary is S3. You can choose any knot that you like in S3, and now we're going to say that this knot is slice if you can find a D2 that it bounds in here. And a first comment or complaint that you should have is that suddenly I'm talking about surfaces in a 4-manifold, and there's different categories I could be working in, and I actually want to pay attention to 2 for most of this talk. So we say a knot is smoothly sliced if this is a smooth embedding, and we say that a knot is topologically sliced if this embedding is just a reasonably nice homeomorphism. I'm not going to make that precise, but you should think it's not space filling. There's no cone point singularities, nothing like that. So there's 3 notions here for a knot to be trivial, and of course they inform each other. Knots are smoothly sliced. You can just use this disk, and if you forget a smooth structure, you get a nice homeomorphically embedded disk. The first thing I want to point out, or sort of assert to you, is that none of those converses are true. So topologically slice does not imply smoothly slice, and smoothly sliced knots are not all knots. And I want to say a little bit more about these non-implications. And let me start with non-implication B, because this will also help us get at, like, what does it actually mean geometrically for a knot to be smoothly sliced? Like, how could you draw a knot in S3 and think about it bounding a disk other than in this, like, stupid case? So let me start unpacking that with a warm-up that you don't need my help for, but we're going to go through anyway. So I'm going to show that there are S1s, so the knot's the same dimension, but I'm going to drop the ambient space. So there are S1s embedded in S2, which are sliced, so which bound disks embedded in B3. Okay, so you all could just do this, like the equator's a great example, but let me do this in a sort of special way. So I want to think about S2 as being the board, compactified at infinity, but don't worry too much about that. And I want to start by taking some stick in the board. Okay, so now what I want is an S1 and S2. And I'm gonna build that by starting by taking an arc gamma with both endpoints on my stick, and in S2 up to isotopy, there's not too many ways to do that. All right, so now what I want to turn gamma into an entire S1, and to do it, what I'm going to do is I'm going to rotate this stick by pi, so it sweeps out of the board into the room we're in until it lands up back in the board over here. Okay, and now this whole thing is an S1 in the board, but I also claim it comes with the disk. And the disk is going to be everything that arc swept out while you did the rotation. That's a very particular disk for this arc in B3.
Sorry, so B3, that's on our side, that's our room. Okay.
Yeah, that's right. And we're sort of compactifying at some infinity that's out there. Okay, so this is kind of the warm-up toy example, but now for real, we can do the same thing, which we won't be able to visualize, but we can sort of write down. So now we're going to think about trying to build a knot in S3 that's slicing B for the actual case. So again, we're going to think about S3 as being three-dimensional space around us, compactified somewhere, don't worry about it. Again, we take a stick, and again, we're going to take an arc with both endpoints on the stick. So now there's choices about how maybe you want to do this. What have I done? So maybe you want to take something like that. And we'll turn this into a knot, again, by rotating our stick. So it's not the rotation you can see. You have to write this down in coordinates, but rotating it so that this sweeps into a B4 until this lands back up in the board where it'll look like this. And now what we have is this S1 in three-dimensional space, and in fact we can just write down this disk that it bounds in B4, which is swept out by this rotation.
So, rotation in R4, isn't it defined by the planes here, or what? Well, what is this rotation?
Yeah, so I'm not sure I'm prepared to write it down on the nose coordinate-wise, but it's really an analog of maybe you want to take sort of a three-dimensional half space and sweep it so that it, sort of the way I would define.
But the stick shouldn't be two-dimensional now to define a rotation. I just naively.
Yeah, right. So this stick really does, you do want this stick to live in an S2 that you're using to define the rotation, I think.
I must say I'm confused just how to understand how your rotation works.
Yeah. I must confess.
Is it an S1 action?
Yes, it's an S1 action.
So S1 actions are defined by planes, right? In R4.
Mm-hmm.
Are they not?
I think we should be able to take a B, like what we're really thinking about is taking a B3 and crossing it with I. The rotation is sort of this spin. Like I'm thinking about it as being a rotation by kind of fixing one of the S2s in the boundary of the B3 and pushing the other one, but you could just think about B3 cross I if you like. So maybe the picture you might want is like, here's a B3, and your arc gamma lives in here. And we'll cross B3 with I to get B4. And then you can cross this arc to something like that. So this arc cross I is a D2. This whole thing is a B4. And now to think of this as a rotation, what I'm doing is I'm taking sort of the front half of the boundary of this B3. So that's the boundary of the B3 is an S2, but I'm just taking the front part and sort of shrinking the interval.
Maybe let me ask you a more direct question. So that plane around which I rotate, this plane intersects my S3 by a line or by a plane? I mean, it's inside S3, or is it?
It's inside S3. Okay. Yeah, it's sort of exactly this in the boundary of this 3-ball.
To be honest, the drawings don't tell me anything, but maybe that's different for other people.
I think that, so if the rotation sort of doesn't make one happy, this picture is sort of even more kind of precise and coordinate-wise. What we're really taking is like this, like we've really drawn a 4-ball here. It's honestly a B3 cross I, so it's definitely B4. And our knot is this arc, that arc, and then just kind of the product between them. So that's definitely in S3. And then when I take the product of this arc on this side and push it, well, that's an arc cross I, so it's definitely a disk in the 4-ball. And maybe that's sort of more hands-on than the rotation thing. Happy to take more questions about it. Happy to draw like this product picture a dimension down. That's helpful. Yeah, let me draw the product picture a dimension down. So here, when we can literally draw this, here's honestly D2. We can cross it with I to get honestly B3, which looks like a cylinder in this picture. Okay, and now if I had my half of a butterfly arc up here, its other half lives down, let me not try to dash it, lives down here. And we take this sort of butterfly product, and well, how does the boundary of that disk hit the boundary of this B3? It's in sort of one half of the butterfly, the other half of the butterfly, and then these just two boring vertical arcs. So that green on the boundary is my knot, which, so this is the shrinking thing. I'm sort of pretending this boring part doesn't exist that's on the stick. And we see the disk in the interior. More questions? So if you want, you can, I claim, sort of write this down as a rotation where you think of, instead of crossing with I, sort of, if you want, cross with I and then shrink one half of this, so that instead of really doing a whole cross, you sort of push at the elbow. That's what the rotation. Okay, so this is how you get a smoothly sliced knot that's not the unknot. And why is this smooth? Well, because sort of we can write this down just in terms of like coordinates and everything is very nice. So you can write this down as smooth structure. So that's sort of this non-implication B. Non-implication A, I'm actually not going to say anything elucidating about. You originally needed work of Friedman and also Donaldson to prove this. That's 2 Fields medals. It's a little much for the first 5 minutes, but this is a really important fact, and I'll be coming back to it. So that's what it means for a knot to be slice or trivial in concordance. But just like in classical knot theory, we don't just study like, is there a knot, the unknot, yes or no. We actually study knots up to isotopy, right? There's an equivalence relation. In knot concordance, we have an equivalence relation as well. So we're going to say that knots K0 and K1 are concordant, which we'll write K0 tilde K1. If, well, let me sort of write it down, and then I'll draw you a picture for how to think about this. So if there exists an annulus, which is an S1 cross I, embedded in S3 cross I, so that the annulus restricted to S1 cross 0 or 1 is Ki, which lives in S3 cross 0 or 1. Okay, so what does this look like? What are we trying to do? We're trying to compare 2 knots. So knots are always going to live in S3. So here's 2 copies of S3. And this one contains our knot K0, and this one contains our knot K1. So we'd like to compare these knots. What we'll do is we'll take a very boring cobordism, S3 times I, between the ambient spaces, and then we'll say that the knots are going to be equivalent if they co-bound an annulus in here. And maybe a sort of quick sanity check, S3 times I doesn't have any first homology. So these knots definitely co-bound something, and the restriction here is that they not have any topology. And maybe a second quick sanity check is, again, I have a surface and a 4 manifold here, so just you want to know what category I'm working in, and again, I can be working in either. And perhaps a final, another comment about this definition is that you want to observe that it does sort of naturally generalize this notion of triviality. In particular, a knot is slice if and only if it's concordant to the unknot. And maybe to see one direction of that, if you just pretend that this is the unknot down here, then you can stick a 4-ball down to the bottom S3 here. Your unknot certainly bounds a disk down here, just like that boring one. And now what are we looking at? This whole thing's a 4-ball that your top knot bounds a disk. So something that I think many people, certainly I had impressed upon me quite a lot as like a very young person, is that maybe your favorite monoid is the set of knots up to isotopy. They have this addition, it's connected some, but you do not have an inverse, it's just a monoid. And one of the really exciting things about knot concordance is that it's not a monoid, it's a group. So the set of knots. And this is true in either category. And I'm not going to prove this, but if you want to prove it as an exercise, a hint is that we've actually already seen where the inverse is going to come from. It's going to come from something baked into that example. And this is a very interesting group. So some things we know about it is that it's abelian. It was proven not very long ago that it's kind of big. For example, it has a Z infinity summand. That's work of Ojwast-Sabo. And it has some torsion. It has 2 torsion. And if you have any other questions about this group, you're free to ask them, but I'll warn you that they're just all open. We don't understand this space very well, and trying to understand this group better is sort of a very active field. You're shopping around for something to do with your life, yeah.
Is there a slice knot that is prime?
Is there? Yes, there is. That's a good question. For example, the knot in the tables is called 6-1 is slice. More questions?
This infinity part doesn't have a torsion, so is it on the other part of the group?
Yeah, we don't understand the other part of the group very well. Though, let me say that actually, you could kick this up to, we even know that there's a z to the infinity summand. So we have both of these. But then everything outside of this is a big mystery. For example, like, it's conceivable that there's like a Q subgroup. It doesn't kind of make any sense geometrically, like how something would kind of rationally be sliced, but we can't disprove that either. And nobody expects any other torsion, but we can't prove that. More questions?
So you said you don't expect any other torsion, but why is there two torsion then? Where is it coming from?
So there are knots that are something that's called amphichiral, meaning that they are isotopic to their mirror. So you take the knot, you change all its crossings, you actually get the same knot back. And for example, this knot has that property. This is the figure 8 knot. And if we look at this proof, what we're seeing here is that a knot connects its mirror. The mirroring comes from the fact that kind of when you outward normal both of these 3 balls here, well, that one will look like it's going the wrong way. So what this argument really shows is that a knot connected its mirror is slice. And so if you start with a knot that is its own mirror, then 2K is.
Wasn't there also a factor of Z4?
There is a factor of Z4 in algebraic concordance. You might hear more about that from Anthony later. In smooth, we don't know. I don't think we expect it. Sort of I think what you're referring to is that the invariants show a 4 torsion.
Maybe just one technical remark. When you go away, they don't see your follow online. But
okay. Well, I'm
sorry.
Yeah, that's why you can keep yelling at me. More questions? Maybe a comment is that, right, so this is the easiest way to get 2 torsion. Actually, it was open for a long time whether this was the only way to get 2 torsion. And that was just disproved last fall, that there are knots that aren't concordant to amphichiral that are nonetheless 2 torsions. It's sort of an active area. Okay, so that's the basics of knot concordance, and it's very nice. But I don't actually care that much about knot concordance. These are not the questions that I get up for in the morning. What I'm really interested in is 3 and 4 topology. And something you learn really early on in your life as a 3 and 4 manifold topologist is that you are not going to be able to get out of doing a whole bunch of knot theory. And the reason for this, to me, is that every time you set out to build yourself a 3 or 4 manifold to study, there's basically always a knot or a link cooked into the construction you're using. And understanding those knots or links helps you understand the manifold, and ignoring it is just shooting yourself in the foot. And this is like a very well-established connection. For me, this is the reason why anybody would want to study knot theory, though other people disagree. And what I want to sort of try to say today as sort of the thesis of the talk is to give you a little bit of understanding how knot concordance is maybe the right part of knot theory if what you're trying to study is smooth 4 manifolds. So the plan for today is to give you 3 applications of this sort of connection that go in the direction I care a lot about. So studying four manifolds using not concordance, and somewhat begrudgingly, I'll give you one application going the other way. All right, to do that, I'm going to back up a little bit and say a couple of words about four manifolds to give us some starter examples to study and ask kind of what kind of questions do people like to study. Let me pause for questions. Anything more about concordance before I do?
Sorry, the nodes you considered are all on-oriented or oriented?
That's a great question. So I'm being sloppy and hoping nobody would call me out on it, but when you do not concordance, you better orient your knots. In fact, yeah, you're right. Yeah, so in fact, they're both oriented and signed. Like S3 has an orientation on it, which gives us sort of a sign on our knots, but then you're right, I really need my knots themselves to be oriented, and you want to sort of ask that these things are coherent. More questions? Okay, so let me start by saying something vague about what's so great about dimension 4. And the reason is that it's the most complicated dimension where you don't start to get classification theorems. And the reason that in higher dimensions, the geometric reason that in higher dimensions that you can get classification theorems, the reason that surgery theory works, geometrically is that for simply connected, let's say high dimensional, let's say even dimensional manifolds, you always have embedded spheres generating your middle dimensional homology. And that's the thing that makes surgeons happy and gets things moving. And in dimension 4, you don't have that. So for me, looking geometrically at four manifolds, what I want to study is look at simply connected four manifolds, look at their middle dimensional homology and ask what kind of surfaces represent it. Like the failure to find a sphere there is the geometric stuff that makes 4 interesting. So one of the big motivating questions is given a homology class in some smooth four-dimensional manifold, and for the rest of the talk, my manifolds will all be simply connected. Determine the minimum genus of a surface which embeds smoothly in your manifolds and generates the class you were given. And there's other versions of this question. You can look in relative homology. You can specify that maybe this has boundary and it does something in particular, but let me just say it like this. So getting your hands on this is sort of, to me, the geometric way of getting your hands on what is so weird and interesting about dimension 4. So I want to start by giving us some really simple four manifolds that nevertheless can give us an interesting answer to this question. So to start, let me just try to build any four manifold that has some H2. So here's how we're going to do that. And these will be kind of the foundational, or the primary four manifold we'll study today. They're called knot traces, so a knot trace is going to be a four manifold which I'll denote x of k. Let me write a technical-ish definition here. So it's what you get by taking the four ball and gluing to it the tube handle along your knot with the zero framing. But don't worry too much about that. Let me show you a picture of how you should think about these. So you start with the four ball because that's a good place to start building a four manifold. You identify any knot you happen to be interested in its boundary. And now we're trying to build something with some second homology, right? So that we can answer this question. And if this was like alg top 1 and I told you to make some second homology happen here, what you would probably do is you would take like a two-cell, a two-dimensional disk, and stick it on here. And that's exactly what we're going to do. So take a D2, its boundary is S1, and identify that boundary with this knot here. So that's a cell complex, it has some H2, very good. It only has one problem right now, which is that it's not a manifold, but we can fix that by thickening this up into dimensions. and this is what a knot trace is. If you know what this means and you want to pay attention to framings, I'm using the 0 framing here. If you don't worry about it. Okay, so some more comments about these manifolds. They're smooth. You can just write down a smooth structure here. This is all very nice. They're compact. They have boundary. They're homotopy equivalent to S2. You can just sort of deformation retract this to a point, this to the central of this. So they're these really straightforward little things, but they're interesting enough. So it's a theorem. It's not stated like this, but originally due to Fox and Milner in the late 50s, that there exist knots such that the trace, this 4 manifold on that knot, has no, it doesn't even in fact have a topologically embedded S2 generating H2. So big enough to get somewhere. And this paper, this is the main theorem of this paper, by the way, and this is the paper where they give the definition of knot concordance. So this is what really sort of kicked off the study of knot concordance. And this is a really important theorem. I'll come back to it later in the talk, but I actually want to start off by talking about an even more foundational result in the field, which is not the main theorem of this paper, but the first paragraph of this paper, which is something that's now called the Trace-Embedding Lemma. So knot traces are great because they're simple, but they demonstrate this weird behavior in dimension 4, but they're also great because they demonstrate this connection in a really important way. So what the lemma says is that traces exactly characterize sliceness. So a knot K is slice if and only if its trace embeds in S4. And in fact, this lemma works in both categories. And it also works if instead of S4 you happen to like R4. So I want to sketch a part of the proof of this lemma because it's so nice and foundational. Before I do that, let me check for questions.
So just to make sure again, so those traces, they have boundary, right?
They do, yeah. Okay, so I'm going to sketch the top implication in the forward direction, and I'm going to talk about it in a second. So what are we assuming? We're assuming that our knot is smoothly sliced. So let me draw, again, a schematic picture of this. This is slightly different from the one I've been drawing. So this is the 4 ball is vertical, but it's meant to be its S3 boundary. This is where our knot lives. And because it's smoothly sliced, we have some disk for our knot over here. And because this disk is smooth, we actually have an entire sort of tubular neighborhood for this disk. All right, so that's just a picture of the hypothesis. Now what I'm trying to prove is that this trace embeds in S4. And to do that, for one, I just want to get an S4 somewhere in this picture. But to do that, I'll take another B4 and glue it to the boundary of this one to get S4. And now I'm looking for a manifold like this embedded in here, and I have one. It's this 4 ball, this thickened up disk, and notice that they're stuck together along our knot. If you're watching framings, there's something to check here that it's 0, and otherwise don't worry about it. Questions about that? It's very cute. It has this nice tidy statement. It's basically the observation that gave birth to the field, but it's also really powerful. Here's the corollary. So it's a corollary, essentially, of the lemma. R4 is exotic. So let me remind you, if you don't know what this means, we say that a four manifold, a smooth four manifold, is exotic if there exists another smooth four manifold, which is homeomorphic to your guy, but not dipiomorphic to your guy. And let me also remind you that people care about exotica. For example, the remaining Concordance conjecture exactly posits that S4 is not exotic. So I want to sketch a proof of this, because it's lovely and it's really just an application of the Trace-Embedding Lemma twice. Before I give the sketch, let me give a historical remark. I didn't write an attribution on this corollary. It's not due to me, but every time I do put an attribution on this corollary, that person finds me eventually and yells at me. So what seems to be true is that this corollary was sort of known to everybody who spent time at Berkeley in the late 70s. Casson hasn't, like, other people will tell you maybe Casson, but in any case, this has been sort of well known. Any questions before I give the proof? So you start off by taking something from the concordance people. You're going to consider a knot K, which is topologically, but not smoothly placed. Okay, that's non-implication A over there. So these are sort of sophisticated objects, but this is something that since the 80s, concordance folks can just give you. Armed with that, we can apply the trace-embedding lemma at least once. So the trace-embedding lemma tells me that the trace on K embeds topologically in R4. So let me get a picture of that going. Here's R4, dashed to remind you that it's not compact. And we have our trace in here somewhere. And I'm drawing my trace with sort of a point to remind us that this is just a topological embedding. Okay. So since I have this embedding, I can consider its complement. So we're going to let Z be R4 minus that trace. And let me make a couple of comments about Z. For one, it's non-compact. That's because R4 is non-compact. I actually only want to cut out kind of the interior of this trace, though. So this is a non-compact four manifold with boundary. You see the boundary of the trace here. And also, the primary thing I want you to observe about it is that this is only a topological manifold. So R4 has a standard smooth structure. This trace has a smooth structure, but it's just a homeomorphism embedding them. So the complement doesn't inherit a smooth structure in any nice way. Okay, however, there's this really magical theorem of Friedman and Quinn, which tells us that all non-compact four manifolds emit some smooth structure. So I can find a smooth structure on Z, and I'm just going to call that object Z smooth. So armed with this Z, I can build the thing that's going to turn out to be our exotic R4. What it's going to be is you take Z, the smooth one, and you glue the trace on K back to it. All right, so this is a smooth manifold, this is a smooth manifold, this is the theorem of Moise that these patch together nicely, and this comes out to be a smooth manifold. So now I need to try to show you that this is homeomorphic to R4, but not dipiomorphic to R4. Let me break for questions before I do.
Maybe just you said, what did you say about the gluing? Why the gluing is good?
There's a theorem of Moise that says, in fact, that there's only one smooth structure on a 3 manifold that are isotopic. So both of these induce a smooth structure on their boundary, and it agrees. So when you paste them together, you're happy.
So basically, that's from some toolbox that we do not control, right? But basically that's some statement similar to what you mentioned on Donaldson, right?
Yes, I mean, I'd say things are even worse than that. We really don't know how to, like, already this is a bit out of control. Yes. Okay, so let me start off by trying to argue why this thing is homeomorphic to R4. And the argument's just going to be, let's go through how we built it and only have our topological glasses on. So what did we do? We considered Z, which was R4 minus this not trace. And then, okay, this is just smooth stuff, we can ignore it. And then how did we get W? We just stuck the not trace back onto Z. So topologically, this was the do nothing construction. So W is just homeomorphic. Okay. So why is W not dipiomorphic to R4? Well, I want to make an observation, which is that the trace on K is embedded smoothly in W. And it's one of the building blocks of this object. And so now, if W were dipiomorphic to R4, then the trace-embedding lemma would kick back in and would tell us that, well, then the trace on K would embedded smoothly in R4, that would make K smoothly slice, which it's not.
Just maybe one more time to make precise. So how many uncontrollable statements are we using here, or just to list them, right?
Yeah, sure. So yeah, the primary thing that we really do not have our hands on is what is this smooth structure here. And I actually think that the movies, like the pasting isn't so bad. So this is out of control, but what Friedman and Quinn do is they just sort of start trying to build a smooth structure here, and every time they have a problem, they push it out to infinity. So the smooth structure near the boundary is like not too wild, and it's gonna, I think, paste together here. Okay, so it's really just this.
And the existence of knots which are topologically but not smooth.
There you go again. Though that's right. Though, yeah, it's a different thing. There's still It's still Friedman giving you the nonsense here. So two. Okay. More questions? Yeah. So I have a question, which again is going to go in that direction. Like, which parts of this do we not understand? And in that direction, like, why doesn't this work for S4? That, well, this theorem of Friedman and Quinn just does not apply. And it doesn't just not apply, it's false. There's plenty of non-compact 4 manifolds without smooth structures. Okay, so we just can't do this line. But like, this is the Poincare conjecture. We should try really hard. So, it doesn't completely stymie us that there exists some non-compact 4 manifolds that don't have any smooth structure. I don't care if there are some. I just want to know that I could put a smooth structure on one of these for S4. So sorry, let me back up again. Why not? When I say why not S4, why doesn't this proof work for S4? What I mean is, we have a trace-embedding lemma for S4, so I could come over here and just try to run this again, where I put S4 everywhere. I had R4 before, and this will be the first thing that breaks down. Question?
It's compact.
Thanks. Compact. More questions? Anything else that's wrong? Okay, so this line drops out, but I'd really like to know that whether these particular in this case, compact 4 manifolds could ever emit a smooth structure, never mind whether there's just some other compact 4 manifolds that don't. And unfortunately, even in the specific case we care about, you can't always get a smooth structure. So there exist 4 manifolds which come from the exterior of a topologically embedded knot trace in S4 without a smooth structure. Okay, so even in the specific case we care about, you can't always have a smooth structure. But again, like this is the Poincare conjecture, we should work really hard. I don't even need to know that you can always put a smooth structure on this complement. I really just need one topologically but not smoothly sliced knot where I could get a smooth structure on this complement in the compact setting. But unfortunately, even that doesn't look good. So there are, for all but 2 known topologically but not smoothly sliced knots, we in fact know that every single complement of any topological embedding of that trace into S4 doesn't.
Sorry, so you're saying for all but 2 known, that does it mean that those known are like a family, or what is there is a list, or what's
Yeah, I mean there's not, because this is sort of a sensitive object, there's many families of topologically but not smoothly sliced knots known, but for almost all of them we know that there's no smooth structure anywhere. Yeah, the sort of literature on these things is not that, there aren't that many families. So this thing down here is like, this is explaining what goes wrong when you try to run this proof in the compact case. And what's really going wrong is building this piece right here, which ultimately means what's going wrong is building our candidate. We just don't manage to get this thing that's homeomorphic. It's R4. If we did, though, for some other reason, then this last line right here, this works just great in the compact case. This is just applying the Trace-Embedding Lemma. And so that final observation, that this argument would work if you could get through the constructive half and you just needed to run the obstructive half, is something that's called the concordance approach on the Poincare conjecture. So let me write that down. So what this approach says is that if you want to disprove this conjecture, what you should do is you should find yourself a knot K such that 1, the trace on K embeds smoothly in some homotopy for a sphere. So over there, I sort of actually proved sort of explicitly that the 4 sphere we built was homeomorphic to S4. Here, let me sort of just demand that you hit the right algebraic topology and then remind you that Friedman says any such thing is homeo to S4. So getting your alg top right is good enough. And then secondly, I want K to be not smoothly sliced. And one of the reasons people are excited about this approach is that there's possibly an invariant here. So it's conceivable that something called Rasmussen's S invariant could obstruct this. And sort of what we have lots of obstructions for showing that a knot is not smoothly sliced, but many of them will vanish if your knot has this property, but this invariant and a few others like it it's possible that they're not fooled by one, so they could still work in the presence of two. And this is what people say is so exciting about this approach, because when you try to just disprove the Poincare conjecture kind of straight up using a four-manifold invariant, the first question is, what four-manifold invariant are you going to use? And the answer is, we don't have any that could do that. It's sort of known that all of our straight-up smooth four-manifold invariants don't work or make sense for homotopy series. So what's supposed to be so exciting about this approach is that you have an invariant. Let me pause for questions.
Yeah, maybe you can return a little bit. So the question is to what disprove the smooth Poincare conjecture.
Yeah. I mean, at least I'm sort of asking, like, try to use this argument to do it and see what goes wrong. And what went wrong is doing the constructive thing. And so the approach over there is meant to say, well, let's suppose you could just do the constructive thing by some other method. You just had this trace embedding, I don't know why. Then you'd be in good shape. Okay, so people are excited about this approach, but I have some concerns about it. So let me try to tell you what they are. And to do that, let me tell you just a little bit of a history of exotica. So this is one way to work on the Poincare conjecture, is just to try to do this, I guess. But another way to try to work on the Poincare conjecture is just try to produce any closed exotica. Closed here meaning compact, no boundary. And that's something that people have been chipping away at. So the first examples follow from work of Friedman and Donaldson in the early 80s. So they just show that there exist closed exotic X4. In fact, they don't write this down explicitly. The first proof in the literature is due to Gompf, and his examples are pretty big. Maybe B2 is like 22 or 23 or something. And then people did a lot more, and we know a lot more. And the state of the art now is a theorem of Ahmedov and Park from 08, who showed that a very simple manifold CP2 connects two copies of CP2 bar is exotic. Okay, so that's pretty cool. And in the meantime, I'm not going to give you a full history, but a lot of stuff happened along the way. Like, we developed a bunch of tools.
Sorry, may I object? This is, I think, not very visible. Maybe.
Not very visible. Bigger would be better.
No, I mean like the color.
The blue.
Yeah,
Great.
blue.
So along the way, we get sort of good at producing large meaning it has a bunch of algebraic topology, closed exotica. But what we don't do along the way, even though we are now very good at producing exotica and we have lots of tools for it, is ever produce any exotica using an approach like this. Which I find to be a really glaring oversight. If this is supposed to be like our shining beacon of hope for the Poincare conjecture, it would be great if it could ever be used to prove anything which hadn't been demonstrated. So one of the first results I want to state is that you can use the concordance approach to ever do anything. So slightly more precisely, and this is joint with Ciprian Manolescu and Marco Marengon, is, let me just give a sample statement. We prove that 3 copies of CP2 and, I forgot, 20-something copies of CP2 bar, yeah, 20, is exotic. Which was known. What's exciting is that we did it using this approach. And we can do other things. This is just a nice sample. Questions about that, about the statement?
Like 3 and 20, like what's the origin, roughly speaking, what's the origin, especially of 20, right?
This, essentially. And the 3 is important because we're going to use a Bauer-Peruta invariant, which wants B terms to be 3, not 4. More questions? Okay, so before we go to break, let me state one more theorem. So now that, I mean, well, let me advertise something, which is that this is not a very good, our proof of this is somewhat terrible. Like, you really don't learn almost anything from our proof other than that this approach like can work. So something I'd really like is more theorems that say this, but that give a better proof or something that's actually more elucidating. And also get smaller, maybe a new, for example, exotic result, even if it's not going to be this one. But it's also fun to get ahead of yourself. So once you know that this can do anything, maybe you just want to skip ahead and try to do this. So the second theorem I want to tell you is not this. That would be a different talk. But going in that direction, and this is joint work with just Ciprian. Or really the central question of this paper is, how would you try to do this systematically? So let me state the theorem as we give a systematic method for producing, basically for doing item 1 here. Homotopy 4 spheres, which come with a trace embedding. So there were methods in the literature for producing homotopy spheres, but they don't come with a trace embedding. And it's not easy to just find a trace embedding if you're given some homotopy sphere. And in fact, I think there was only 2 examples of homotopy spheres in the whole literature that anybody had ever found a slightly interesting trace embedding in. So what we do is give a systematic method for doing the first thing. And once you can do that, you can start looking at what you get and trying to do the second thing. And we don't get the most exciting thing we could get, but you do start to find some stuff. So for example, we show that we find these 5 topologically sliced knots such that if any of them were smoothly sliced, then the Poincare conjecture would be false. Okay, and this should seem a little bit like a logical inversion from the concordance approach here. I'll explain why that's the statement after the break. Maybe a final comment before the break is that the point of this work, if it wasn't going to be a tremendously exciting work, was just to get the field started on being able to do this maybe systematically. And the good news is that happened. The bad news is that this second line is no longer terribly relevant. There's a hopefully forthcoming theorem of Nakamura saying that our 5 knots are not smoothly sliced. Okay. Which is what we expected to happen. In fact, it's sort of great. He gives a new method for obstructing sliceness to do it. And just one final comment is that, so he obstructs the 5 knots that we happened to find when we studied kind of one big family, which I'll tell you a little bit about. But his method doesn't work in general. So it's quite possible you could even just sort of do what we did for just another set of examples and find another 5 knots where Kai's argument doesn't apply. Questions, and I'll stop there for the break.
We're not smoothly sliced.
In the Nakamura statement? What we show is that if any of them were smoothly sliced, then the Poincare conjecture would be false. Yeah.
Any more questions?